Hello students, welcome to the channel Statistica Hub. This is our lecture number 12 in the course SH201A probability distribution for the probability theory. So in this particular lecture, we are going to go over the topic that is the Poisson distribution. This is like a very important distribution, like widely used. Okay, so let's start with the discussion. So I will start with very generic example, like how you can observe like what is a Poisson distribution. So you can think about like if you go for the binomial distribution, in that one you said that you are having maybe n number of trials and you are counting total number of success, correct? Total number of success. Fair enough, that's that could take the value. Maybe number of success can be 0, it can be 1, it can be 2, it can be 3, and so on, it can be n. Okay. Now, in that particular part, and if you go for the Poisson distribution, there is like a little bit difference. So the difference is something like this. In spite of n fixed number of trial, if I go for the n, that is coming out to be infinity. Okay. Assume that like this is my house and there is a window just maybe in front of me. Okay. And there is a road. So there are a lot of vehicles that are crossing over the road, right? A lot of vehicles are passing by my window. Okay. And if I count like a success to be maybe some accident, okay, a saddest person, maybe for me the success is like some particular car or the vehicle that is getting into some accident, that is a success for me. So in this particular part, in a particular time zone, let's say from 6 a.m. to maybe 6 p.m., I'm sitting on my chair and just looking outside my window. So in this particular slot, there are like infinite number of vehicles that are crossing my road. Okay. In this particular part, if I say I'm counting total number of success, total number of accidents that I may see in this particular day, then we know the number of trials, every vehicle that can meet an accident or may not meeting the accident, right? So you are having the setup that one vehicle that is coming up, it may be in the accident or may not be in the accident. You can count success, you can count failure. Okay. So the number of trials that I'm having, that is coming out to be infinity. And if you go for the success, like what is the probability that a particular car or maybe some bike that is going to meet some accident? So we know the probability is like very, very low. But it is nothing like very, very low, mean to say like it is very, very, maybe very close to zero, but it is not exactly zero. But some particular day, I may be seeing some accident, right? The possible thing. So the idea behind this thing is when the number of trials is coming out to be infinity and the probability of success, if that is coming out to be very, very close to zero, then this x that was supposed to be some binomial distribution n comma p that can be approximated by some Poisson distribution with you say lambda. Lambda being the parameter. So lambda is the parameter in the case of this particular distribution, the Poisson distribution, and this is your average rate of occurrence. So in this particular part, if I just go for the basic idea, then you can simply observe that the x that can be 0, that can be 1, that can be 2, and that can be infinity also. So this is some sort of like particular distribution. Like till now, we covered the binomial distribution. We covered the Bernoulli distribution. In this one, the range set that was containing only 2 elements. In this one, the range set that was containing n plus 1 observations, correct? But if you go for the Poisson distribution, the number of possible values of the x, the range set, that is coming out to be countable, but it is infinitely countable. Okay, I hope that makes sense. So you know this is also a discrete random variable, but in this one, the support set or the support of the random variable that is coming out to be infinitely countable set. The first thing. Okay. Now, if you go for the probability distribution, let's say probability x equal to some k, that will be lambda raised to the power k, e raised to the power lambda minus lambda or k factorial. Okay, that is the probability function, and you can see the k that can be 0, that can be 1, that can be 2, and so on. The rate parameter, it must be having some particular features. So it is the average rate of occurrence. So technically, the average rate of occurrence that will be coming out to be something that is positive. Okay, it can't be negative. So the parameter space for this one that will be coming out to be lambda belonging to 0 to infinity. That is the parameter space. Okay, so that's how you go for the Poisson distribution. Okay, the basic idea, the basic definition and something you can say. Okay, then for the Poisson distribution, the mean will be coming out to be expectation of x, that will be lambda, and the variance that will be coming out to be lambda. So this is a particular distribution for which you have to memorize. Like in the last, we just covered that the variance will be smaller than the mean. But in this particular part, the mean will be coming out to be exactly equal to the variance. So just remember this property that for Poisson distribution, the expected value of x that will be exactly equal to the variance of x, and both are coming out to be lambda. Okay. Now, if you go for the derivation of this particular part, like how I'm going to get the value of expectation of x, then you can simply go for the derivation. Let's say expectation of x. So that will be summation k running from 0 to infinity in this case, k into probability function x equal to some k, correct? Okay. This is the probability function that is given at this place. So you can simply make use of that one. So k running from 0 to infinity, k into lambda raised to the power k e raised to the power minus lambda over k factorial. Correct? Now, if we just try to solve this particular part, so if you simply observe maybe this particular portion, then you can see we can solve it somehow. Okay. Or maybe if I just combine this part also, I can simply write this to be summation k running from 0 to infinity. This factorial term, this will get cancelled out. From this one, I can take the lambda to be common. So I can go for lambda that can be common. And if I go for lambda raised to the power k minus 1 now, or k minus 1 factorial, and we are having e raised to the power minus lambda. But you know, when we are going for k minus 1, so it can't be like 0. There will be starting from the 1. So we are getting this thing. So the thing is, you can take the lambda to be common. So lambda is common, k running from 1 to infinity, and lambda raised to the power k minus 1 over k minus 1 factorial, and e raised to the power minus lambda. And you can simply observe this particular thing. That is nothing. That is the probability mass function of Poisson distribution. And we know the total probability, like summation k running from 0 to infinity, probability summation, that will be coming out to be 1. So eventually I'm getting lambda. So that's how I'm going to get the mean of the, or we can say what I'm saying. Yeah, the mean. Okay. Or in the other sense, you can just simply think about maybe this particular part. If I just go for this part, or I can go for a generalized format, just go for this particular thing, summation I running from maybe 0 to infinity, and lambda raised to the power I over I factorial. What is this thing? This is just the expansion of e raised to the power lambda. Correct? So from this part also, you can just go for lambda e raised to the power minus lambda, and that will be e raised to the power lambda. Cancelling out, I'm left with again lambda only. Okay, so I hope that makes sense, that we are going to get the expected value that will be coming out to be lambda only. Okay, then you have to go for the variance. So the derivation for variance, that will be little bit lengthy. So let me add one page maybe. Okay, so we have to go for variance of x. So that will be nothing. That will be simply we are going to get like expectation of x square minus expectation of x raised to the power 2. Okay, that's what we have to find. So to calculate all of these things, these are not very, very simple. So we will go for first the derivation of this particular thing, expectation of x minus 1. Like I'm going to combine the things, so I can simply think that is nothing, expectation of x square minus x, right? That is the idea. We are going to find this particular part. So if you go for this derivation, summation k running from 0 to infinity, and we are having x or maybe k, as we are using the k into k minus 1, and probability function x equal to some k. Okay, start inputting the values. So I'm going to get k running from 0 to infinity, k minus 1, and we are having lambda raised to the power k, e raised to the power minus lambda, or lambda k factorial. Yeah, that's what I'm getting. Okay. Now, again, if you go for like simplification, like canceling out the things, taking the lambda to be common, so you will be getting, it will be coming out to be lambda square e raised to the power minus lambda summation. And from this one, we are taking two parts common. So that will be k starting from 2 to infinity. And that will be lambda raised to the power k minus 2 over k minus 2 factorial. That's what I'm going to get. Okay. So we are going to get something. So again, you can just think about the same case, whatever we just covered earlier. So that particular part, again, this particular part only, that will be coming out to be e raised to the power lambda, just from the similar concept, like the expansion of e raised to the power x. So that get cancelled out. I'm going to get lambda square only. Correct? This first part, that is coming out to be lambda square. Okay. Now, if you have to go for like this particular thing, expectation of x square, so that is nothing, that is expectation of x square minus x. Okay. And you can just go for expectation of x. So this part you already got. So this part is coming out to be lambda square. We need this part that we already derived. Okay. And we have to go for variance of x. So that will be expectation of x square minus expectation of x raised to the power 2. Okay, so that will be coming out to be lambda square plus lambda minus lambda square. Cancelling out, I'm left with only lambda. So we came to know that in the case of like x that follows some Poisson distribution with parameter lambda, you are going to get the expected value of x that will be coming out to be lambda. And if you go for the variance of x, that will be coming out to be lambda. So remember this property. Okay, so that is something about like finding the mean and the variance of a Poisson distribution. Okay, I hope that makes sense, like no doubt in this particular part. Okay, so let's move ahead now. So we have to go for maybe, let's move ahead. Okay, then I have just given some basic idea, like given some basic idea, like how to solve this thing. And I have already given the proper derivation, so you can follow that one. Then you go for the MXT. Okay, the moment generating function. So that will be e raised to the power tx and the expectation of that particular part, simply going for this particular thing. So again, if you just go for the similar kind of derivation, you are going to get the mxt that will be coming out to be e raised to the power lambda, e raised to the power t minus 1. That will be the mxt, and you have to memorize this one also. Okay, so that's how you can think about the proper thing. So I ask you to go for the derivation of this part. Okay, try the derivation for this particular part once you cover this particular lecture slide. Okay, moving ahead. Then we are having certain examples like how you can see the Poisson distribution in the real world. So the number of emails received per hour. So in a particular day, you may not be getting any particular mail, right? The number of success, the number of mails that you are going to receive, that can be 0. On the other hand, on some certain day, you may be getting 1 mail, there may be 2 mail. And on some certain day, let's say my team, my people, if they are having some particular mails and they are going to go for spam kind of thing. So they may be sending like emails like every minute, every minute. So in that particular part, you may be getting like infinite number of mails, right? So that's like one example. But you know, like the getting the very less number of mails, that is like very high chance. So that means to select the lambda that is coming out to be low. Okay. The number of cars passing through a toll booth in a given period of time. Again, the same thing on a certain day or in certain particular point of time, there may not be any particular car. Okay, on weekends, maybe there are a lot of people who are crossing by the road or going for some vacation or something. So you may be finding like a lot of vehicles that are crossing that particular toll plaza. Okay, moving ahead, you are having the number of decay events per unit time from a radioactive source. Yeah, in this one also, you may be having like infinite number of radioactive decays. So that is the idea. So these are some of the examples. Now there is some particular example kind of thing, maybe very basic example that you can think of. So if a call center receives an average of 5 calls per minute, so the lambda that is given 5 per hour. Okay, then what is the probability of receiving exactly 3 calls in the next hour? So technically they are saying x equal to 3. We have to find this probability. So probability x equal to 3, that will be simply lambda 5 raised to the power 3 over e raised to the power minus 5 over 3 factorial. Okay, simply if you solve this thing, you are going to get this particular value. Okay, along with this, like in the last slide also, I missed out one thing. You may go for the CDF also and simply follow the definition that the CDF for a random variable, that is probability x less than equal to the x. Okay, that is your fx at this particular value, the CDF. So if you go for this particular distribution, maybe the Poisson distribution, then that will be coming out to be summation x running from 0 to the particular value, let's say x. I have to go for the greatest integer function, and you have to go for like the probability function e raised to the power minus lambda, lambda raised to the power x over x factorial. That will be the CDF. Just focus on, I am writing the greatest integer function because this is a discrete case, and if you go for maybe 3.5, so it will be counting the probabilities of x equal to 0 plus x equal to 1, x equal to 2, and x equal to 3. It is not going like beyond that one. So we have to go for like the greatest integer function. Okay, or if you simply write x also, then also it will be making sense because we know if you go for any discrete like other values, maybe x equal to 0, 1, 2, and if you take any other value other from this particular thing, then that probability will be 0, correct? So that's how you can just write this particular part. Okay, remember this thing. Okay, moving ahead then there are some applications. So when we are having some events which are very rare, So for that particular part, the probability of success that is very, very low. Okay. And maybe you're looking for like infinite number of cases. So in that particular part, you can think about a Poisson distribution. Okay. It is used in the field of like telecommunication, traffic engineering, and natural sciences. Okay. Number of mutations in a given stage. Okay. These type of examples can be there. So if you are taken up any particular course in the maybe Markov chain stochastic process, then you may have encountered the Poisson process also. So in that particular part also, like a Poisson distribution that is defining a complete class of like understanding. So it is very important distribution. So you have to remember what is a Poisson distribution. Okay, so this was just the recap. So whatever we just covered, we covered the definition. We covered like how a Poisson distribution is framed, like what is the meaning of a Poisson distribution, certain properties like finding the mean, variance, expectation, some results that you have to memorize, and the importance in statistical modeling. So that was all about lecture number 12. I hope you're able to understand the concept of Poisson distribution. So thanks. Bye.